Let's take a look at two reactions and compare them. In our first reaction, we have lead 2 chloride reacting with lithium sulfate to produce lead 2 sulfate and lithium chloride. When we look at this reaction, we've got a compound reacting with a compound, which makes it what kind of reaction type? It's a double displacement. So our lead is going to displace the lithium out of this compound and produce lead sulfate. And the lithium is going to displace the lead out of this compound and give us lithium chloride. So we're looking at a double displacement reaction. We've got the same types of atoms on both sides of our equation, but we're basically just rearranging the atoms. So we've got a chemical reaction. If we look at our second reaction, aluminum is an element, iron 3 oxide is a compound. We're going to produce iron, which is an element, and aluminum oxide, which is a compound. So now we've got an element reacting with a compound, which is what kind of reaction type? Okay, we're looking at a single displacement reaction. And since aluminum forms positive ions, it's going to displace the positive ion out of the compound. Or, remember our trick, since aluminum is on the left-hand side of the staircase, it's going to displace the left-hand ion out of the compound. So we're going to produce iron and aluminum oxide. So we're looking at a single displacement reaction. But again, we've got aluminum on both sides, iron on both sides, oxygen on both sides, so essentially we're just rearranging the atoms. Now in addition, if we look at this reaction, not only is it a single displacement, but it's also a redox reaction. Because aluminum is a free element here, so it has an oxidation state of 0, but it's in a compound over here, so it's going to have an oxidation state of +3. Iron is in a compound over here, so it's got a +3 charge, and over here it's a free element, so it's going to be 0. So not only can we classify this reaction as single displacement, but it's also a redox reaction. Now let's look at a new kind of reaction. Okay, this is something we haven't seen before. There's a couple things that are different about it. The first thing is we've got these numbers here, which we've seen before way back at the beginning of the year when we talked about atomic structure, but we haven't really looked at it since then. And we've got these numbers on the bottom as well, and those didn't appear in the reactions up above. In addition to that, we start with nitrogen atoms and helium atoms, and we end up with oxygen and hydrogen. So unlike the reactions up on the top, here we're changing the identity of the atoms in the reaction during this particular process. So the second reaction is a different, or third reaction is a different kind of reaction type. So let's look at this and kind of review a little bit. Remember that the N is our symbol, and then we've got these two numbers. Our first number, we should remember, is our mass number. And the mass number tells us how many protons and neutrons there are in that particular atom. The number on the bottom is our atomic number. And the atomic number identifies the number of protons in the nucleus of that particular atom. And remember that the number of protons in the nucleus of an atom identifies what element the atom belongs to. Now, we talked about what isotopes are, and isotopes involve our mass number. And when we look at isotopes, isotopes are atoms of the same element that have a different number of neutrons. So when we look, if we have a different number of neutrons in isotopes of the same element that have the same number of protons, our mass number is going to be different. And remember that the number on the periodic table, the atomic mass, is the weighted average of all the different isotopes of a particular element. So let's go back to this reaction for a second. We've got nitrogen reacting with helium to produce oxygen and hydrogen. Our mass number on nitrogen is 14 and our atomic number is 7. For helium, our mass number is 4 and our atomic number is 2. For oxygen, our mass number is 17 and our atomic number is 8. And for hydrogen, our mass number is 1 and our atomic number is also 1. So when we look at a reaction like this, we're looking at a different branch of chemistry. And we're talking about what's called nuclear chemistry. Nuclear chemistry involves the nucleus of atoms. And what we're going to see is since there are changes in the nucleus, there are going to be changes in the identity of the elements. So we talked about what isotopes are. Now we want to talk about specific kinds of isotopes, which are called radioisotopes. And when we look at radioisotopes, they are atoms of a particular element that have an unstable nucleus, which means that their ratio of protons to neutrons in that nucleus makes that nucleus unstable. And what it leads to is what we refer to as radioactivity. And radioactivity is a way that an unstable nucleus tries to become more stable. It's the spontaneous disintegration of an unstable atomic nucleus, and in most cases we're going to see some kind of emission of radiation, and that's why we call it radioactivity. Now, there are several types of radiation, and we're going to go through these 4 types in our examples. Our first type is called alpha particle radiation, and our symbol for alpha kind of looks a little bit like a fish. But in reality, what it is a helium nucleus that has an atomic number of 2 and a mass number of 4. The charge on an alpha particle is +2, and essentially what we're looking at is a helium nucleus. So if we look at a reaction and it tells us that we've got alpha particle decay, this is what we're going to be giving off in order to make the nucleus more stable. If we deal with beta particle radiation, our symbol for that is a B. Essentially what we're looking at is an electron. So we're going to use the symbol E. Electrons essentially have 0 for their mass and a charge of -1. If we look at positron emission, we're going to be looking at a positively charged particle, a positron. It's got a mass of 0 and a charge of +1. And if we look at gamma radiation, what we're dealing with isn't particle, but we're dealing with energy. High energy electromagnetic radiation is emitted. So the rules for writing equations for nuclear reactions are basically twofold. The first thing is that the mass number, the number on the top, has to be conserved on the reactant and the product side. And the second thing in writing nuclear reactions is that the electric charge also needs to be conserved on both sides, or the atomic number needs to be the same on both sides of a reaction. So let's look at some examples. Okay, if we talk about these types of nuclear reactions, we call them transmutation reactions. They're called transmutation reactions because we're actually going to be changing the identity of the element. So let's look at our first type, alpha particle emission. So that means that we're going to be emitting or giving off alpha particles during this type of nuclear reaction. So if we look at this example, we've got polonium-211. This is our 84. Sometimes you see that there, sometimes you don't. You can look that number up on the table, periodic table, if it's not there. If it's emitting an alpha particle, we know that alpha particles are a helium nucleus with a mass of 4 and a charge of 2. So we know that the mass needs to be conserved and the charge needs to be conserved. So if we've got 211 on this side, we need a total of 211 on this side. So 4 plus 207 will give us 211. But this number isn't going to identify what that polonium transmutated into. We look at the atomic number, and that'll help us identify. We've got an atomic number of 84, so that means the total on the product side needs to be 84. We know an alpha particle has a atomic number of 2, so 2 plus 82 would keep that atomic number conserved. The 82 we look up on the periodic table, and it tells us the identity of the element that the polonium transmutated into. So it transmutates into lead 207. So let's look at this example. Let's say that we're told that radon 219 goes through alpha particle emission, and we want to figure out what that particular radioactive isotope transmutates into. Well, we know that it's going to be an alpha particle decay, and that you would be told. So we just need to figure out what it's going to transmutate into. So we need to figure out 4 plus what gives us 219, and 2 plus what gives us 86. And the atomic number is going to identify what the element is. So see if you can figure that out. All right, so 4 plus 215 will give us that 219, and 2 plus 84 will give us 86. Now we're going to look up on the periodic table what element 84 is, and that'll identify the element, and we're going to have polonium. So let's look at our next example. Let's say that we are told that we're looking at beta particle emission. And if we look, we start with bismuth 210, and if it goes through a beta particle emission, we can figure out what it transmutates into. 0 plus 210 will give us 210. Minus 1 plus 84 will give us 83. And then the 84 we look up on the periodic table, and we can identify the element that it transmutates into. So again, let's look at an example. Let's say that we're told that francium 223 goes through a beta particle emission, and we want to identify what it transmutates into. Okay, so if it's beta particle emission, we have to know that that's our beta particle. And now we need to figure out what it transmutates into. So figure out what your mass number will be, what your atomic number will be, and then use your periodic table to identify what element francium 223 transmutates into. Okay, so 0 plus 223 gives us 223. Minus 1 plus 88 will give us 87. And when we look up 88 on the periodic table, we're talking about the element radium. Okay, so let's say we've got a positron decay, and we're told that carbon 11 goes through positron decay. Okay, so we write out what our positron is. Our mass is conserved, so 11 equals 0 plus 11, and 6 equals 1 plus 5. And the 5 tells us that we're transmutating into boron 11. So we've got something called K-capture, which is just a little bit different. Instead of emitting a particle, we're capturing, or we're adding this particle into the nucleus this time. So if we have K-capture, we're going to put that particle as a reactant. It's going to bombard into the nucleus and change the particular element, or transmutate it. So 100 plus 0 gives us 100. 46 minus 1 gives us 45. And when we look up 45 on the periodic table, we know that we're looking at rhodium. So let's say we've got rubidium 83, and we're told that it goes through a positron decay. We can figure out what it transmutates into. Okay, so we've got 0 minus 1. So 83 plus 0 gives us 83. 37 minus 1 gives us 36. And we're looking at krypton.